So we're going to get into that more. Okay, so to begin with, I just took some stuff out of the book. This is mainly testing vocabulary is what this is. What this problem says is, it says, is this an antiderivative of this? Well, how would you know? What is an antiderivative? It's the opposite of a derivative, right? Okay, well, if you want to find an antiderivative, there's a couple of ways you could do this. One way to do this would just be to see if you took the derivative of this, would you get this? Okay, that's the idea. So let's go ahead and let's take a derivative of this function. I'll show you another thing on this that I want you to know too. Okay, let's just go ahead and let's take the derivative of that. Now, how would you do that derivative? What rule? Product rule. That is a product rule, right? Okay, the first piece is this. You can think of that as the first function, and that is the second function like that, okay? So the idea with that, hold on, I'm not doing this right. You know, I just noticed something. I'm like totally spaced out here this morning, okay? I'm doing this wrong, okay? Here's what you should be doing is you should be seeing if we do the integral of this, do we get this? Okay, now we don't actually have to work the integral out because technically you guys wouldn't know how to do that integral yet, okay? And you never will learn probably. That's more of a Calc 2 kind of thing going on right there. So really all you can do is take the derivative of this and see if it's this. Remember the way you check the answer to an integral is you take the derivative, right? And you see if it takes you back to the beginning. So I was doing the wrong thing. So what you need to do is you need to do the derivative of this, and then you want to see if that gives you this expression right there. Okay, that's the idea. So remember, if we do an integral of a function, we're trying to get an antiderivative of that right there. Well, let's see. Yeah, this one right here you'd use a product rule on. I don't think there's any way you would get this, but let's try. Let's go ahead and do a product rule on this. So the first is x squared and the second is e to the x. Go ahead and do a product rule. So remember that's the one that goes first, derivative of second, plus second times derivative of first. You don't need to write that down because hopefully you know that by now. Okay, so let's do that. So you'd have x squared. What's the derivative of the second? E to the x, okay. Now we go backwards, e to the x, what's the derivative of the first? 2x, okay? Well, the thing on this is, it looks like you're not going to get the same thing. The only thing that you could even do with this is you could factor an e to the x out. You could factor an x out also, but you're not going to get this. So the answer would be no, this is not an antiderivative. I'm going to go ahead and just take out an x and an e to the x. Like that, okay, and if we do this, you would have an x left there, because x times x is x squared, and you would have a plus 2 there, okay? But the thing I want to show you on this thing is clearly not that thing. So the answer to this problem is no, it's not an antiderivative. What you guys want to get real solid as you're learning about integrals, when you get an answer to an integral, this is not the answer of the integral, then the derivative of this would have to be this. That's what an antiderivative is. You're doing the opposite thing, okay? A simpler example that you'd understand better would be something like this, okay? Do you guys know what the integral of x squared is by now, just within 2 or 3 seconds? X the third over 3, okay? That's what we were working on last week, okay? Well, the idea is if you do the derivative of this answer, then you'll get back to the beginning. That's what I was trying to show you on this problem. So if you do this derivative, that would be 3x to the second, you know that by power rule over 3. Derivative of c is 0. So see, that would take you back to the beginning. That's what I was trying to show you on the previous problem. Does that make sense? Okay, so the answer on that first problem is no, that's not an antiderivative. That's the idea, okay? All right. Let's see on this one. So we're going to look at this the same way. So the question is this an antiderivative of this? So what we're going to do is really what this question is if we did the integral of ln x over x dx, the question is, would we get this? Okay, and there's two ways to do this. One way would be to work this integral out. You could work that integral out by U-substitution and do it that way. The other way would just be to take the derivative of this and see if it takes you back to the beginning. So let's just do this way. Let's just do the derivative of this alleged answer that we're trying to see if this is an antiderivative. Okay, let's see if this takes us back to the beginning. So what is that antiderivative supposed to be? ln x over x. That's what we're seeing. I mean, if it is, the answer is yes. If it isn't, the answer is no. Okay, so how do you do a derivative of ln x to the second? That's kind of like a power rule, exactly. You'd bring the 2 down. It's a chain rule is what it is. So when you do that, that's a constant. So that comes down. Okay, now think about how you do this. Now you're going to do times 2 ln x to the first power, then what? Chain rule.
1 over x.
There you go, 1 over x. You got to do the derivative of what's inside, so I'll put the 1 over x there. Of course, the derivative of 10 is 0 like that. Okay? Well, let's see what happens. Notice on here, if you double a half, you get 1. This is 1 times ln x times 1 over x. Well, if you multiply that straight across, look what we get. We get ln x over x. So that does match this. So that means the answer is yes. Okay, that's how that goes. Okay? That's just really, like I say, it's a vocabulary exercise. It's basically, do you know what an antiderivative is? Okay, does that make sense to everybody? Yeah.
So on there to explain, how would you?
I think my math is my explanation. I think what you could say on there is, like on the first one, you could say the derivative was not equal to f of x, capital F of x. On this one, you could say the derivative was equal to capital F of x. Okay, but really the math is explaining that. Okay, all right. So let's go to the next page. I think there's a couple of more things we want to do. We're just barely in this class. You just barely learn differential equations. I don't really know how much you might encounter that in your major. It depends certainly on the intensity level of what you're going to study. If you were going to study economics, yeah, you would certainly deal with this, I know. But it just sort of depends a little bit on what you're going to do. So what we're doing on this is a differential equation, and all we do is touch this. And really, if you're an engineer, if you're a math major, you actually take classes in differential equations and study it. You can study it very much in depth. But the idea is, the reason this is a differential equation is because it has a derivative in it. So if you have an equation, an equal sign, and somewhere there's a derivative, then it's a differential equation. So what we're going to do is we're going to solve this. If I say find the family of antiderivatives, that just means you're going to have that plus c in there. You're going to have a whole bunch of, it's going to be off by a constant. So here's what you do. You want to find m. In this particular problem, you're wanting to find what the function m is. Okay? So that means that what you do is the opposite of a derivative is, okay, where did that function come from? So you integrate to do this. So what you're going to do is you're going to do an integral of dm over n, and then we're going to use a dn because that's the variable that is in the function. M is the name of the function, just like you're used to seeing y the name of the function, n is the variable. And then we're going to do the same thing on the right side. We're going to do the integral of 10n, n squared minus 8 to the 7 times dn. So if you're going to, and this is the only kind of differential equation you'll learn how to solve in this class, is you've already got a derivative, you've got the answer to the derivative, you're working backwards, you're finding an antiderivative, that's why you're doing the integral, okay? All right, what do you think the integral of dm over dn is? M, okay, what did we do? If you do the derivative of m, you get dm, right? Okay, so that's going to be m. That's the reason we did that. Okay, now we got to focus on doing this integral right here, 10n n squared minus 8. So what we learned last class is how to do U-substitution integrals. The thing about this integral right here is we don't have a product rule for integrals. That's real important. What you have to do is you got to use this U-substitution. So the idea would be, you want to set u will have to be something, And then when you take the derivative of u, it should be close to the rest of the integral. Okay? So let's see. This sometimes takes students a little time to catch on to, so I'm going to show you what the correct thing to set this equal to is this. And the other thing I'm going to do is I'm going to have you just pull that 10 out. And you can erase that if you want to, just on your paper, or scribble that out. That's the best way. If you got a constant, just pull it out. Okay, so we're going to do that. So what you want to write down is you want to write down that u is going to be equal to n squared minus 8. Okay, if we let this thing become u, would you be able to integrate u to the 7th? What is the integral of u to the 7th? Power rule for integrals. U to the 8th over 8, right? Okay, so if we let that thing become u to the 7th, you can do it. Now, if you do this, this is what we were talking about. Usually I teach this, I kind of highlight this. What we're hoping is when we get du, that we end up with n dn or something very close. So what is the derivative of n squared minus 8? 2n. Okay, and then you also got to do the 2n times dn. That's the notational bookkeeping device is about all I can explain for now, okay? Well, we wanted that to be n dn. So what can you do to this equation that would get rid of the 2, so it would just say n dn? Divide by 2, exactly. Okay, so what you're going to do is you're going to divide by 2. Best way to do this is just kind of think of that as 1/2 like that. Okay, so what we're going to have, let's just write down, we have 1/2 du equals n dn like that. Okay, that's what we learned how to do last time. This sometimes is hard for students to catch on to until you do some homework on this and practice a little bit. So see, the idea is that's going to be u. Your integral is going to say u to the 7th, and then it's going to say 1/2 du there, which is going to be easy to do. Okay, so let's go ahead and let's write down that integral then and complete this. I'll just write this at the side. So the integral is going to be this. We have the 10 already there. Okay, what are you going to replace the n squared minus 8 with? U. So that's going to be u to the 7th, right? What is n dn? It's 1/2 du. Okay, that's what you got to understand is everything has been accounted for in our integral. Okay, what I highlighted in yellow is this part. Okay, what I highlighted in blue is this part right here. Okay, that's it. Does that make any sense? That's what we were working on last time. You're going to have to roll up your sleeves to do homework to get this down. It's the only way to learn this. Now, what would you do with the 1/2? What's a good thing to do with it? Take it out. Exactly. That's a constant. So you'd have 10 times 1/2 integral u to the 7th du. Okay, now what is the integral of u to the 7th? U to the 8th over 8. Good. Okay, so and then if you do half of 10, you're going to get 5. So that's going to be 5 u to the 8th over 8 plus c. Okay, but that's not the answer. What you got to do at the end is you got to plug this u back in. So that's going to plug back in there. And then the final answer on here, I'll just kind of write this at the bottom because I'm running out of room here. So the final answer is going to be 5/8, and then I'm just going to plug the u in, which is n squared minus 8 plus c. Okay, that is the final official answer to that differential equation. And it was an integral, and it was a U-substitution integral. Okay? Now, if you wanted to determine if you're right, which is super important when you're learning math, how could you tell you're right on this problem? 100%. You would take the derivative of your answer, and you would see if it matches that. Okay? I'm going to do that at the side. You don't have to write this down. You can just pay attention to this if you want to. So I'm going to do the derivative of 5/8, n squared minus 8 plus c. Okay? And let's see, I think that whole thing was to the 8th. I left that off. You guys need to get that in there too, because that was 5/8 u to the 8th. Okay, so that's your answer, that's to the 8th. Okay, if you did this derivative, you'd write the constant down. You would use a chain rule on this part, so you'd bring the 8 down. You'd have n squared minus 8 to the 7th, and then what would you have to do? Chain rule would be integral derivative of what's inside, so you'd have that. Okay, derivative of c is 0. Notice the 8's cross out. Notice you have 5 times 2 is 10. You got 10n n squared minus 8 to the 7th. Notice that matches, so you're right. So you take the derivative of your answer, and if it's correct, then you got the answer right. Okay, and that's what you got to do when you learn integrals. You got to learn how to tell that they're right. You have to. That's the only way you begin to understand this. All right, does that make sense what I did? Hardest thing is that U-substitution thing. That's what we were working on last time, okay? All right, let's go ahead and do one more of these, and I think the applications I'm going to do are going to be dealing with this also. Okay, this is the same way. This is dy over dt. That is a derivative. You're trying to find the function that has this derivative. So you can think of the right side as the derivative. Okay, you're trying to find where that derivative came from. Okay, so just like the last problem, we're going to do the integral of both sides. Okay, and let's see, on this side, we're going to do integral of ln t minus 5 over t minus 5, and then we're going to use dt. Why dt? Because the variables match up. The expression has a t in it, so dt is what you're going to have like that. Okay, now with this one, sometimes you can do an antiderivative in your head. If you do this one, we're going to do a U substitution on this. What is the left side going to become? That's the easy part. That's just y. Okay, the integral of a derivative is, okay, the function. So that's y. Okay. Now what we want to do is we want to work with U substitution on this. Now remember, whatever you set u equal to, when you do the derivative, it's got to give you what's left over in this thing. So let me ask you if you have any idea what I could let u equal to. T minus 5. There's not too many choices, is there? So let's try that. And remember, you know, sometimes you just try something. So the idea is going to be, okay, that thing's going to be u. I would end up with ln of u if I do that then, okay? Which can be a little bit of a problem. Okay, now what we're wanting to happen on du is we're wanting du to be what's left over. Well, let's find out, okay? So I didn't quite do the u right. Now here's why. Because what is the derivative of t minus 5? That's just 1, okay? Well, that's no good. Okay, we tried. But there, you can work this problem out. There's another way to do this. The best way to do this is to do this. Let u be equal to ln of t minus 5. The whole thing, the whole entire thing, like that. Okay, and let's see what happens now. Now, what do you want du to be equal to? What I highlighted in blue, right? Okay, what is the derivative of ln of t minus 5? It's 1 over t minus 5, and then really, by chain rule, the derivative of t is 1, although it doesn't make any difference. dt. Look at that. It's what I'm left with. Because that's what you have. So you have a 1 over t minus 5, if you want to think of it that way. So what you're going to have then is this whole thing right here is going to be u. This whole thing right here is going to be du. You've got everything accounted for in the problem. Okay? So your integral is going to be the integral of u du. That's it. Okay, that whole thing right there is u. That's what we let it equal to. And then this thing is du. Does that make sense? Okay. All right. How do you integrate u to the first? That's easy. U to the second over 2. Good. So that integral is u to the second over 2 plus c. What else you got to do? Got to remember to plug the u back in to get your final answer. Okay, so what you would have is you would have, and you'd have to write it like this, you'd have ln of t minus 5, whole thing to the second over 2 plus c. Okay, and then I'm just going to write this down. So we got y there is equal to, and this would be your final answer. Okay, so the hardest part of that problem is the U substitution. This is a difficult thing for students to gain a grasp of until you really start practicing it. And it's like anything else, you'll get it down. Okay, now I'm not going to do this, but how would you tell you're right on this problem? You would just take the derivative of your answer, and what would it have to be? What you started with. Okay, and that's a real important part of the problem, is you want to be able to do that. Check every time you do something, okay? All right, any questions about that? Does that U substitution make sense? Okay, some of you are shaking your head, some of you are looking funny. Okay, all right. Okay, well, we're going to do a couple more of those. The rest of these are application problems, but they are really talking about the process is just about the same. Okay, so what this is see, I've given you on this example a marginal revenue. Remember, a marginal revenue is the derivative of the revenue. So let's go ahead and start by just writing that down. We have r prime of x is 40 minus 0.02x plus 200 over x plus 1. Okay, that's the differential equation we're going to find. Now, what you're finding is you're finding the revenue function. Okay, so what you're going to do on this is just like the previous examples I did. We're going to do the integral of both sides. Okay, maybe we can, sometimes you can do integrals in your head, sometimes you got to do U substitution. It just depends on the situation. Okay, all right, left side's the easy part. What is that? R. Okay, remember you're doing the opposite. The opposite of a derivative is just the function. So that's r of x. Okay. Now this one, remember we learned that if you have an integral of sums and differences, well, you can break it up. So you probably want to do this like this, and I want to put the notation of dx in there. So let's just do the integral of 40 dx, which is easy to do. And then we can do the integral of 0.2x dx, which is also easy to do because it's a power rule. And then the last one, you could do in your head, or you could do U substitution on it. Okay, so let's do that. Okay, so a couple of things I'm going to do on this then. Okay, I'm going to bring down the r of x like this, and I'll just kind of put you on the spot and see what you know. Okay, what would you take a derivative of that would just give you 40? 40x, okay, so that's easy, okay? If you forget the rule, just understand what you're trying to find. Okay, what kind of rule would apply to doing an integral of x to the first?
Exponent.
The power rule, okay? Add 1 to the exponent, divide, like we learned last time. See, that constant can come out of the integral. I'm not going to write that down, but you can just bring that out and write it down. And what's the integral of x to the first? X squared over 2, okay? You want to be automatic on spotting that and able to do that. So we got that. Okay, now this next one is the one that's a little hard to see, but you could, just think about this, you can bring the 200 out, so the 200 would be a part of the answer because that's a constant. I want you to try to think of this and try to do this in your head. You could do this if you think about it the right way. Can you think of anything that you would take a derivative of that would give you 1 over x plus 1?
ln.
Ah, good. Okay, ln. Now it's the ln of x plus 1. Okay? A lot of times if you have 1 over something, there's a good chance that that's a ln going on. And yeah, that's what the derivative of that is. Okay? So that's just going to be 200 ln x plus 1, and at the end of this you got to put the plus c. So see, we didn't have to use U substitution on that. All of those things could be processed in our head, which is nice. Okay, now that we're not done with the problem because you've got what we call an initial condition on this. So one thing it says on here is it says it's giving you this. You always expect this to be the case on a revenue function. And I always just explain it this way. This just means if you sell nothing, you get nothing, right? So if your business doesn't sell squat, you don't get any money, right? So that's what that's saying. Now this will allow you to get C. That's what that's going to do, is help you find C. So when you have a statement R of 0 equals 0, that is your X value, that is your Y value. It's just like you have a point 0, 0 on the function. So what you're going to do is you're going to replace this with 0. That statement says the revenue is 0 when X is 0, okay? And be careful about this. A lot of times you can do this in your head, but you still need to be really careful about this, okay? Particularly with this natural logarithm on this. So what we're going to do is I'm just replacing every X with 0, and I'm replacing the revenue with 0. So notice the only unknown we have is we have a C. So we're going to solve this for C, then that will give us a particular solution to the differential equation. Okay, so what do we have? That's 0, that goes to 0, that goes to 0. We have 200 ln of 1 plus c. What's ln of 1? 0. So what we really have is 0 equals 200 times 0 plus c. So what's c? 0. And it's not always 0. A lot of times it is. You do got to plug that in and verify the details. So what you would have is, let's write this kind of like this, what we would call the particular solution, okay, would be this. It would be r of x, and we're going back to this antiderivative. It's really this thing right here, except c is 0. So your particular solution would be 40x, and then you could divide out that 0.02 and 2, and that would give you minus 0.01x squared plus 200 ln of x plus 1. Now you don't have to put the plus 0 there. I'm just putting it there because that's what we took the time to find. Okay? See, anytime I give you an initial point, then you can find c. If I don't give that to you, then you just have a family of antiderivatives. Does that make any sense? Okay, and I got one more part of the problem. Now, this is the easy part. So how do you think you'd do this? I want you to find the revenue if you sell 1,000 things. Now what do?
Plug 1,000 in.
You plug 1,000 into that antiderivative, exactly, and this would be just something you'd use a calculator on. So let's do r of 1,000. So that's going to be 40 times 1,000 minus 0.01 times 1,000 squared plus 200, and then that would be ln of 1,000 plus 1. And then you can just go to your calculator. I'm just going to... Am I missing something? Oh, the 0.01 came from here. See, when I did my antiderivative, I got x squared over 2, but I already had that 0.02. So I just divided it out. If you take 0.02 over 2, you get 0.01. You might not have caught that. Okay. All right, so let's see what we have here. You guys can put it in and check me if you want to. Okay, so here's what I'm getting. If somebody doesn't mind checking, because sometimes I don't see very good. That's what I'm getting, okay, as a revenue of $31,381.75. I just put it in one step. I mean, I just did 40 times 1,000 minus 0.01 times 1,000 squared plus 200 ln of 1,001 is what I did, so I think I'm right, okay? You got that? Okay, it's always good for somebody to kind of double check. All right, very good. Any questions about what I did? Okay, all right, let's do this last one here, and then we're going to start this next one. I try to do a lot of the business applications in here. Our textbook has some science applications too that show up a little bit. This one is, you could think of this as a business piece right here because it's talking about the rate at which enrollment is changing. Okay, so let's write down the differential equation. We have DE, E is enrollment over time, and that's equal to 5,000 t plus 1 to the negative 3 over 2. The condition t greater than 0 is inherent in the problem. Time's got to be positive on this problem. Okay, so we have this. So what we're going to do is, it says if the enrollment is 2,000 now, we're going to find the projected enrollment 15 years from now. Now the first thing you got to do is you've got to get the enrollment function. This is only the rate of change of enrollment. So you're going to start this off like we did the last problem, is you're going to do an integral of both sides. And this integral on the right side is going to be dt because that's the variable, okay? So this one right here might be a good U-substitution integral. I think that's the way that one probably looks, as U-substitution. Okay, tell me what the left side is. E. Now you can write E. I'm okay if you write E. You probably technically it's best to write E of t. Okay, kind of like the last problem I did R of X for revenue. Okay, now one thing you can do is you can bring the 5,000 out. I would generally recommend that you do that. And then we have t plus 1 to the negative 3 halves times dt. And that is a U-substitution integral. Okay, so we're going to focus on the U-substitution. Okay, if we let u, let's just try it. Let's let u be equal to t plus 1. Now see, when you do that, what you got to think in your mind is, okay, if I let this thing be u, then I would end up with u to the negative 3/2. Would this be an integral that you could do? Yeah, it's power rule. You add 1 to the exponent and divide by the result. That integral there is doable. The next question is, if I do du, I want to be left over with whatever else there is. dt. What is the derivative of t plus 1? dt, okay, because it's 1, okay? You know that the derivative of t is 1 and the derivative of 1 is 0, and then you got to put that dt in there. That's your notation, your bookkeeping. So yeah, we got a good U-substitution integral. Okay, so how is your integral going to go? It's going to be what? U to the negative 3/2, and then what's dt? It's du. Okay, everything is accounted for. That's the key is everything must be accounted for. And while I'm at it, I'm going to bring the 5,000 down so I don't forget it, and I'm going to bring the e of t down like that and just kind of keep doing this. Okay, so when we do this, I'm going to do this kind of at the side. If you're doing an integral of u to the negative 3/2 du, what you do is you add 1 to the exponent and then divide by the result. Now, this has got a fraction in it, so you got to take care when you do that. If I add 1, I would use 2/2. That way I have a common denominator. The result of that is negative 1/2, so that's what you got to divide by. Then I'll have the plus c. So that's going to give u to the negative 1/2. Now we talked about this last time, and don't let this bother you. What are you really doing if you divide by a fraction? You're multiplying by the reciprocal. So this really is going to be negative 2 u to the negative 1/2 plus c. Now that's a power rule for integrals. You got the fraction involved in that. Does that make sense to everybody? Okay, it's arithmetic. Okay. Now, what else do you got to do? You don't want u in your answer. What do you got to do? You got to plug the u back in. That's always the last step when you do this. So what you would have is you would have negative 2 times t plus 1 to the negative 1/2 plus c. Okay, that's what you have. So I'm going to kind of take this back. I would kind of do something like that on scratch paper, and then let's go back to where the problem is. We have e of t equals 5,000. We still have that. Then when we did the integral, the result was negative 2 t plus 1 to the negative 1/2 plus c. Okay, and there's one more move you can do on this. You can multiply the negative 2 times 5 to get negative 10,000, and then t plus 1 to the negative 1/2 plus c. You could write that exponent as positive if you want to. So what this is this is what we call the general solution. That's kind of a family of antiderivatives because of the plus c. Okay, so that's the first step. See, on these last 4 problems I've done, we've been doing the same thing. Okay, is there any question so far? I'm not done, but is there any question how I got the antiderivative? What if you wanted to find out if you were right so far? What would you do? Take the derivative. You could take the derivative of the answer and see if it takes you to the very beginning. So that's always a manageable thing to do and a reasonable thing to do. Okay, now what we have on this is it says enrollment is 2,000 now at time equals 0. See, this statement right here gives you a point, 0, 2,000. And what you're going to do with that is you're going to use that to find c. Anytime I give you a point, that will allow you to pinpoint this down and find a specific solution. So what you're going to do is you're going to do this. Okay, you're going to plug in 2,000 in for e of t, and then you're going to plug a 0 in for t. That's it. That's going to allow you to find c, and then there's one more step on the problem. Okay, all right, so if we do that, we'll have 2,000 is equal to negative 10,000 times 0 plus 1 to the negative 1/2 plus c. You've got to solve that equation. Okay, and then this is not too hard on this one, I don't think. So what we would do on this one is the first thing is you would probably want to get this isolated, so you would get rid of the 10,000. Okay, so if you do that, you would have divide both sides by negative 10,000. You could get a decimal if you wanted to on this, which I think is what I'm going to do. Okay, that'll cancel that out. And I'm just going to divide that. All of the zeros cross out, so you've really got 2/10, which is 0.2. So that's really negative 0.2. And then this right here is 1 to the negative 1/2 plus c like that. Okay? What is 1 to any power? 1. Okay, because see what this piece is, if you have 1 to the negative 1/2, here's what it is. It's 1 over 1 to the 1/2. 1/2 is a square root, right? This is really 1 over square root of 1. So it's 1. The answer is that's equal to 1. Okay, so what you're going to have is negative 0.2 equals 1 plus c. Then you can subtract 1 from both sides of the equation. So you've got c. So if you do that, that would be negative 1.2 is what c is. Okay? All right, so see, if you're given a point, which you are on these problems a lot of times, given what we call an initial condition, then you can find c. So that means what you want to write down then, and then we're just almost done with the problem, is we have a specific solution to this problem would be this. Okay, go to your antiderivative, which is here. That's your general solution right there. But what we're going to do is we're going to write this as e of t equals negative 10,000, t plus 1 to the negative 1/2, and then c gets replaced with negative 1.2. So that right there is your specific solution to the problem. Okay, does that make sense? Okay, remember, when you see that initial condition, that just tells you that you need to know immediately, I got to find c. Okay, so there's one more thing. Now it says find the enrollment in 15 years. Okay, so what would you do if you wanted to find the enrollment in 15 years? You just plug 15 into t, and then this would be a good calculator problem, I think. Although I do see, I think it'll square root will work out. So we just do e of 15. So that's negative 10,000, and then that's 15 plus 1 to the negative 1/2 minus 1.2. Okay, and I'm going to clean this up and write this as negative 10,000, 16 to the negative 1/2. And you can go ahead and you can put it in your calculator right now if you want to, exactly the way that is. Or you could work this out. You work out that 16 to the negative 1/2. When you're doing 16 to the negative 1/2, that's 1 over 16 to the 1/2. So it's 1 over square root of 16. Okay, or you can just go to your calculator. That's what I'm going to do. So I'm just going to go exactly like it is. Negative 10,000 times 16 raised to the 1/2. And then you got to do the minus 1.2, and that makes no sense whatsoever. I got negative, that enrollment being negative.
No.
Well, I hope I didn't make a mistake somewhere, just some little mistake somewhere in the problem. Maybe I messed up on C. Did I get C wrong?
Yeah.
Let me double check that real quick. I didn't catch that while I was doing that. Oh, duh. Duh. I feel like really bad. Like it is Monday, but this is like really a bad teacher mistake. And I'm even recording myself too. And it's going to be on YouTube. And I'm going to be embarrassed. Okay, oh, that's all right. Doesn't matter. If teacher makes a mistake, it's good. So here's what I kind of got in a hurry on this. This is 2,000 here. And see, you're not ready to divide that out. You would actually have negative 10,000 plus C. Okay? All right? You can't divide by that. Because see, this thing in yellow is 1. Now what do? You add 10,000. But see, if you make a mistake, you often catch it because the math that wasn't making any sense to me whatsoever. Okay, so we got C, and see, that would be C is equal to 12,000. That's what you said you had. Good. Okay, so that means we need to change a couple of things here. That was a dumb mistake. So we got plus 12,000, okay, and I think we're good. So I think we should get a logical enrollment on this, hopefully. So you want to just add the 12,000, and then we'll see what we get. I think that should work out. Okay, that's much more logical. 9,500 students, okay? So if you make one little mistake, the nice thing about math, though, a lot of times you can, if you're thinking about your answer and whether it's sensible or not, you can catch things like that. What you want to do, okay, you want to think about negative students doesn't make any sense. Okay, so that's the problem like that. All right, so I think this section right here is pretty challenging. It's got U-substitution involved in it, and that's the key stuff here. And then the differential equations is really an application of integration.